Welcome, everyone, to this explainer. I'm going to be your virtual physics teacher today, and honestly, I am absolutely thrilled to guide you through this. Think of this session as your high-yield, ultimate study guide for demystifying mechanical waves. We're going to track the dynamic, totally fascinating journey of energy right from the moment a wave is born to the complex ways it interacts with the physical world around us. So, grab your notebooks, get focused, and let's unlock the secrets of physical motion together.
Okay, let's dive right in. Here's our roadmap. We are going to follow the literal life cycle of a wave. We'll start with the journey of energy, map the anatomy of a wave, figure out how the medium sets its speed, see what happens when waves collide, look at bouncing off boundaries, and finally, we'll tie it all together with the physics of music.
Section 1. The Journey of Energy. Shifting the Paradigm.
To kick things off, we really need to address the very first major hurdle nearly every physics student faces. We need a complete paradigm shift. We have to break the super common misconception that waves are just moving chunks of matter. Here is the absolute core definition you need to remember. Wave transport is the movement of energy and information through a medium without the physical bulk transfer of the matter itself. The wave moves the energy forward while the medium literally just wiggles in place. Think about those massive radio towers broadcasting signals across huge distances. They are transmitting vast amounts of energy and information right to your car antenna, but there's no way they're shooting bulk air or chunks of metal at you to do it.
Let's compare energy flow to bulk flow using a simple everyday analogy. Look at the flowing river example here, representing matter transport. The actual water molecules are physically traveling from point A to point B. But contrast that with wave transport. When a droplet hits a calm pond, elastic forces bind the medium. The water particles just oscillate locally, up and down. Only the energy pattern travels outward. This is a great time to think about ocean waves. The water itself mostly bobs up and down, but the energy travels toward the shore. That's actually exactly why strong ocean waves can be so incredibly dangerous. You aren't just getting hit by water, you're getting slammed by a massive transfer of pure kinetic energy.
Now let's break down this wave typology matrix. Mechanical waves basically come in two physical flavors based on their motion. Transverse waves oscillate perpendicular to the direction the energy is traveling, kind of like plucking a string. And if we compare light waves and sound waves side by side, it gets really interesting. Light isn't a mechanical wave because it doesn't need a medium, but it is a transverse wave. Then, right next to it, we have longitudinal waves, where the physical motion is parallel to the propagation, creating compressions and rarefactions. Sound waves are the perfect everyday example of this, physically pushing and pulling the air back and forth as the sound travels directly to your ear.
Section 2. Anatomy of a wave. The spatial and temporal map.
Now that we know what waves are, we need to build a shared vocabulary. Treat this next part like I'm writing the absolutely crucial terms on the chalkboard for your midterm. Let's do a rapid-fire review of these 4 basic wave properties in order. Make sure you memorize these. First, amplitude is the maximum displacement, basically how tall the wave gets. Next, wavelength is the physical distance between two identical points. Third, period is the specific amount of time it takes for one full cycle. And finally, frequency is how many of those oscillations happen in a single second, measured in hertz.
Let's map those bullet points visually onto this diagram. You can clearly see the wave's peaks, which we call crests, at the very top, and the troughs at the absolute bottom. The amplitude is that vertical distance right from the center resting line up to a crest. And the wavelength is that horizontal span from one crest to the exact next crest. It's a really perfect spatial and temporal map of our disturbance. Notice how our visual anatomy translates directly into the mathematical wave equation you see here. Now don't be intimidated by the math, just look at the visual connections. The A stands for our amplitude. The K contains our wavelength. The omega symbol holds our period. This single equation is just a beautifully concise way of describing exactly where any particle is at any position x at any specific time t. Section 3. The medium sets speed, inertia, and elasticity.
We've built our wave, so let's shift our focus to wave propagation. We really need to ask a vital question. What actually controls how fast the wave's energy travels from its source? Well, the answer is the medium. Speed is determined entirely by the inertial and elastic properties of whatever material the wave is traveling through. It is completely independent of the wave's frequency. Take a look at the transverse guitar string shown here. Its speed relies on the string's tension and mass. Compare that to the longitudinal sound waves in the pipe, whose speed relies on the compressibility of the gas. Simply put, the medium is the absolute boss of speed.
Section 4. When waves collide, the principle of superposition.
Let's move to the next phase of our journey. Interaction. What happens when these traveling waves actually run into each other? I want to pose this question directly to you. Challenge your everyday intuition for a second. When two physical objects, like cars, meet head-on, they crash, they break, matter is violently destroyed. But do waves crash and break when they meet?
The answer is no. Waves do not break. Because they are just overlapping energy, their displacements simply add together algebraically. This is known as the principle of superposition. Notice the upward pulse and downward pulse meeting in the middle of this graphic. In that exact overlap moment, they undergo destructive interference. They temporarily cancel each other out, leaving a perfectly flat line. This overlapping creates complex interference patterns all around us. In fact, it's the exact same principle behind your noise-canceling headphones.
Section 5. Bouncing off boundaries, reflections, and phase. Now, what happens when a wave doesn't hit another wave, but rather hits the physical end of its medium? Let's look at boundaries. The crucial point is that waves reflect, but how they reflect depends entirely on the boundary. Look at how waves reflect off solid walls in this diagram. The wave exerts a force on the wall, and by Newton's third law, the wall pushes back equally and oppositely. This forces a 180-degree phase reversal. The wave comes in as a peak but reflects back as a trough. This is exactly how a sound echo works off a solid mountain face. It's also the foundational physics behind medical ultrasound machines, which use these precise wave reflections bouncing off different tissue boundaries to literally map out the inside of the human body.
Section 6. The physics of music, normal modes and beats.
Let's see how this all builds into the real-world applications we love. All these concepts, speed, superposition, reflection, they combine to create the physics of music. This is exactly how beautiful sound reaches our ears. When waves are trapped between boundaries, continuously reflecting back and forth and overlapping, they create what we call standing waves. Trace the graphic here. Because of superposition, you get these stationary nodes where the wave never moves at all. That's total destructive interference. And right between them, you get antinodes that are oscillating wildly up and down. It looks like a steady, vibrating pattern. These boundary conditions dictate the specific natural frequencies a system can play, which we call normal modes or harmonics. Looking at the first example, we see a constrained system, showing exactly how guitar strings vibrate to create music. The fixed ends must be nodes, which mathematically limits the possible wavelengths. Beside that, we see air columns, like a flute or an organ pipe. Whether the pipe is open or closed changes where the nodes and antinodes fall, which totally changes the instrument's fundamental harmonic frequencies.
And what if two instruments are slightly out of tune? Well, you get the phenomenon of beats. When two slightly different frequencies overlap, they constantly drift in and out of phase. This causes alternating constructive and destructive interference over time. To your ear, it creates a single sound whose intensity audibly waxes and wanes like a wah-wah-wah sound. Musicians actually listen for this exact beat frequency to perfectly tune their instruments together.
To summarize our entire journey through energy, just look at this phenomenal map. The source creates the frequency and period. The medium dictates the speed. When you add boundaries, they form the specific standing waves and harmonics. Together, these elements interact to create the beautiful, mathematical wave patterns that govern everything from giant ocean swells to the symphonies we listen to.
I want to leave you with this final, almost philosophical thought about superposition. After waves cross paths, intertwining in those complex patterns of interference we talked about, they separate and continue entirely unaffected. They move on as if the other were never even present. It's a really profound physical truth about the resilience of energy, which makes you wonder, if massive waves of energy can pass right through each other completely unchanged, what exactly is happening with all the unseen frequencies passing through you right this very second? Keep observing the world around you, and I'll catch you in the next explainer.